So that's one thing, and then the key thing is the Bernstein Bezier polynomial. So in a sense, there's nothing really new here. All I'm going to do is I'm going to take the barycentric coordinates of the point, so it's got 3 components in 2 dimensions. I then work out the power of that thing with alpha being a multi-indices, and then put this binomial or this multinomial coefficient into the good measure. That's it. So these things form a non-negative partition of unity, blah, blah, blah. But there is a couple of natural identifications. So when I talk about a Bernstein polynomial, it's linked with one of these multi-indices. As we showed before, each of these multi-indices is linked with a domain point. So each of these multi-indices has got geometric interpretation as well, and there's the multi-indices. So what we have is a natural identification between the basis functions, the domain points, and the multi-indices. And this is really going back to finite elements 101. This is the way that we draw pictures. When we start to teach finite elements, we draw pictures like this, saying these are the degrees of freedom, and everyone's very happy. But perhaps another problem with high-order methods is that for some reason we go to hierarchic basis. There are good reasons for doing that. But in terms of practitioners and uptake of this technology, I would say that hierarchic bases, well, in principle, I don't see why they're not conceptually simple, have certainly resulted in certain communities not taking up this high-order methodology. They just don't like the fact that the degrees of freedom are not geometrically located. So there's first of all a natural identification between what I'm going to use as my basis functions, the domain points, and multi-indices. So much so that I'll talk about them interchangeably. Now these are not the Lagrange finite elements. I mean, this is not a finite element audience, but if this was a finite element audience, I would have to make a big play